Hello there, this is Ms. Page. This is our final lesson for Unit 8 on exponential functions. We're going to look at some more problems in context, application type problems, and including those that we will be calculating an average rate of change and interpreting that what that average rate of change means in that situation. So one of the things that we will be needing to do is once again to determine if an exponential function is growth or decay. So I want to point out to you that the way to do that is to focus on the base, which is the quantity in parentheses shown here, and the exponent equivalent to the coefficient of the independent variable here shown as x. So b to the power of c, that's our base. And remember that that is then what we use, that value compared to 1 to determine if we have growth or decay. So if that power, b to the power of c, the base, is greater than 1, we have a growth function or growth model. If it is less than 1, but still positive, then we know we have a decay model. All right. So this shares some strategies to help with solving different types of context problems. So some of the things to keep in mind: be aware of how all the variables in the function are defined. What's the independent variable represent? What does the dependent variable represent? Independent being like x, dependent being like y. Definitely make a note of the units, because we've seen some problems before where the quantity that we're given needs to be converted to match the units of how the variable is defined. Always, if you're solving for something, like if you are trying to figure out the value of one of the two variables in the function, then you do need to figure out which of those variables is the one you're trying to find a value for, and what the other variable represents, what its quantity would be. Making sure that you do any conversion of units that would be required. And don't forget that with context problems, you want to make sure that you correctly interpret the math for the situation. All right, so here is the first problem that we're going to look at. So these will be samples. In general, dealing with some common types of exponential models and some of the types of questions that we will be answering for this particular lesson and assignment. So here we have the amount of sodium-22 that is present at a time t in years is modeled by the function s of t. And so we know t is in years, which of course is a time quantity. And remember that function is a word that represents the y quantity, which would be s of t. And the amount of sodium-22 present is modeled by the function. So that is the quantity represented by s of t, or the y quantity. So that's one of the things in a context problem we always want to pay attention to. In part A, we are supposed to determine, is the model exponential growth or decay, and be able to explain our reasoning. A really basic way to explain your reasoning for a problem like this, where you're determining if you have growth or decay, is to use the definition of what the base must be. So if you decide you're going to say that it's a growth, then you should be able to say that the base is greater than 1. If you decide that you have a decay model, you should be able to say that your base is less than 1, but still positive. All right, so here's where we have to understand the structure of our function here, that the base of the power is e, and the coefficient of the independent variable is negative 0.267. So the base for this model is e to the power of negative 0.267. So we need to calculate that power of e and compare it to 1. You can use a calculator. You can also use number sense, but I think probably at this point it is wise for us to also at least use a calculator. If you think you know whether it's greater than 1 or less than 1, then double check yourself using the calculator. So powers of E, remember, are on many scientific calculators, not necessarily because I can't see yours, but on many scientific calculators, the power of E is a second function above the natural logarithm key, which is an ln key on your calculator. And you should notice like mine is in blue, which make above the ln key, which makes it a second function. So I type second ln, and what that my calculator pulls up is E. And so it's saying, all right, tell me what exponent is on this base of E. So now I'm going to type in the negative 0.267, close my parentheses, and hit equals. So this particular value, well, actually, I don't need to round it. Let's just use our ellipses notation. So what I get here is 0.7656 ... Okay, so we can see that there's a 0 in the ones place, so this number is smaller than 1. And so now let me show you how I would answer this problem with the reasoning portion of it. So because my base is less than 1, I know I have exponential decay. So that's how I'm going to start this. So the model is exponential decay. My conclusion. Because, so here's my reasoning. The base of, so I'm going to use my power of E because that was the given base, E to the power of negative 0.267 is about 0.7656, which is less than 1. So this very clearly demonstrates that I can identify and understand what the base is, E to this negative 0.267, that I understand what value that is close to as a decimal, because looking at this right here, many would have difficulty knowing it's going to be less than 1. And then I understand that my decay matches that because that is less than 1. That's why I have a decay model. All right, so part B here. If 300 grams of sodium-22 was present in a soil sample in 2010, how much sodium-22 will remain in 2020? Round to 3 decimal places. You don't need to know what sodium-22 is, but it is a radioactive isotope. And so this is why we have a decay model. So we start with a certain amount, and then over time, it decreases at an exponential decay rate. And so one of the things to keep in mind about the structure of our functions, we've talked about this before, is that this A value is the starting amount of whatever the model is about. So since this is about quantities of sodium-22, then our A would be the beginning amount of sodium-22. So it's always the beginning amount. Here it's the beginning amount of sodium-22. So here our A would be equal to this 300 grams that was present in the earlier year of 2010. So this is a 300 grams. And I'm just going to use the 300, of course, but it is in grams, which means that when I go to figure out how much sodium-22 there is in 2020, it will also be in grams. So this basically means my model is now S of t equals 300 times e to the power of negative 0.267 t. All right, so t, I need a value for t. So from this, I also have to understand, okay, I am looking for S of t. So I need a t value. And t is in years. And so I'm looking at, okay, well, I should not use 2020 because it's not a calendar year that's implied here, but a quantity of years. So my t would be my 2020 year minus my 2010 year to give me a 10-year increment over time that I'm looking at, okay, how much has this decreased over a 10-year period? So now I am calculating S of 10. Like so. So when you put this into the calculator, for the very common scientifics, I use a Texas Instruments 30x2s. So what I would do is type the 300 times, and then I'd pull up my power of E, which remember comes from my second ln on this calculator. And that in my calculator now pulls up this E to the power up. So now inside here, I'm going to type my negative 0.267, and then I'm just going to do times 10. I'm not going to do an extra set of parentheses because if I don't do that exactly correctly with those parentheses, then I could get the wrong answer because the calculator will misinterpret what I want to be the exponent. So my calculation of times 10 is part of my exponent. So I would close my parenthesis after the times 10 and then hit equals. All right, let's see what we get. All right, so we are rounding to 3 decimal places here, which hopefully you remember is called the thousandths place. And so what I have here on my calculator is 20.7756. That's to the fourth. And the reason I went out to the fourth is because if I want to round to the thousandths, the third, I look at the next one. So the 6 tells me that this 5 goes up 1, so it goes up to a 6. And this would be again in grams. So my conclusion will be in 2020, there will be about 20.776 grams, and abbreviation, remember, would be just G, remaining in the soil sample. So over that 10-year period, we started to remember with 300 grams. We're now down to a little bit over 20 grams after that 10-year period. All right, here's a practice problem. I recommend that you pause the video here and try this problem, and then come back when you're ready to check. Let's take a look. So hopefully you came up with an approximate, your base here, this power of E, an approximate value of 1.266, which is greater than 1, which makes it exponential growth. Let's take a minute to do B. So pause the video again. Let's take a look. All right, so this shows how it works out, that A is the 750. That's your starting amount to finish the model. And then here, your time, this uses T. I guess that technically should be an H. Our H is 9 hours and H is in hours, so no conversion was necessary. And then doing the math, hopefully you came up with about 6,256 bacteria. This is rounded to the nearest whole number because bacteria is a living organism, so it makes the most sense. Another practice problem. Again, pause the video, give this one a try. Let's take a look. So here, hopefully you came up with the bird population is increasing, which goes along with this being an exponential growth model. And we can determine that from our base. So our base is this 3.2 to the power of 0.04. which is calculated at about this decimal, greater than 1. So we know that the bird population is increasing because we have an exponential growth model. All right, let's try part B. Let's take a look. All right, so here, at least we use the right variable this time, t. Here we have that subtraction of calendar years and gives us a 14-year time span. And so we're looking to figure out the bird population, what we're looking at the growth over that 14-year period. And now this one, you might have gotten a little bit tripped up by this, but back here in the function, it says that your bird population, B of t, is in thousands. And so that's what this is about. So that means that, like the 9 doesn't mean we have 9 birds. That doesn't make any sense. In fact, if you look at it, the starting amount was 4.8, which doesn't make any sense either for birds. And so what we're looking at is a simplified function that has everything kind of sort of divided by 1,000. So to get it back to the number we really need, we have to multiply by 1,000 at the end. And so you should multiply by that 1,000 before you do any rounding to get the most accurate quantity. And again, this is rounded to the nearest whole number afterwards because we're talking about birds. So it doesn't make sense to have part of a bird. That's kind of gross. All right, so now for the next part of the lesson, we're going to focus on some average rate of change problems. Do keep in mind that these problems are mixed together. So you do have to learn how to, of course, recognize an average rate of change problem and do what's required there versus the problems that we have just been finishing and working on. So remember that when we calculate an average rate of change, which is the change in the function values or y values divided by the change in the x values, where change means the difference, subtraction, over a particular interval of x values, that what we are always really doing is calculating slope. So if you know your slope formula, then you know your average rate of change formula. If you know your average rate of change formula, you know how to find the slope of any line. And so it's the same thing every single time. And for those of you who will be taking calculus, this has a direct relationship between one of the big things that you learn in the first semester of calculus, which is derivatives, and learning what a derivative is, how it's related to back to average rate of change. And when we find, you'll learn about secant lines, and a secant line is simply a line that intersects a curve at 2 points. And so when we find the slope of that secant line, that's what we're referring to as average rate of change. All right, so this problem we will be doing together. And I'm just going to point out, some of the key things that tell me that this is an average rate of change problem. Because like I said, they're going to be mixed together. So notice here it says, what is the average change? Oh, word average, word change. Okay. So that's telling me this is an average rate of change problem. We're looking at what the change is in the insect population per day. And we're given from 1 to 4 days after the application of this insecticide as our interval. So we have to realize that our interval, which is always of our independent variable, like x, here that would be d. So we have this model, P of d, and we know that this model is for an insect population that are treated by this chemical. We know that D is days since the application of the product. Ooh, look at this. We also know that P, which is P of D, is in thousands. That thing that might have tripped you up on the previous problem. So what we've got this model, P of D equals And we want the average rate of change for the interval from 1 day to 4 days after that application. That's the idea. That's what we have to determine and understand from our reading. So now remember, once we have our interval and we know what we're looking for, then it's a matter of calculating the y values that go with each of these d values. So this is a d value, this is a d value. So we need p of 1. So that is 216.8 times 1.8 to the power of negative 2.56 times 1. And we need p of 4, which is going to be 216.8 times 1.8 to the power of negative 2.56 times 4. All right, when you use my calculator, and I just want to do this real quick to avoid people getting confused on maybe why your calculation's not working out. Be real careful with the power. It's not a power of E, so the parenthesis doesn't automatically come up. So like on my TI scientific, I type in 1.8 and then I hit my caret key for my exponent, and then I have to open up a parenthesis, and in that side that parenthesis, show my multiplication and then hit equals. Now here's not a big deal because anything times 1 is itself, but in the next one, it's a big deal because if I don't have those parentheses, my calculator's not going to understand that the times 4 is part of the exponent. So it is a very important thing to put parentheses around those products. All right, let's see what we get for the numbers. All right, so for this first one here, the P of 1. Now remember, I want to round to 3 decimal places in my average rate of change. So best practice would be, if I'm going to use a decimal here, I should carry it out to at least the 5th, maybe even the 6th decimal place to make sure that my final rounding is as accurate as possible to that 3rd decimal place, that thousandths place. So I'm going to write this as 48.146161. Okay. All right. So now for the second one, repeat the process. All right, so now for this one, what I am getting is 0.527313. You might be going, what? That doesn't make any sense, because if you remember, what does P of D represent? What do our Y quantities represent? It's the number of insects that remain after this insecticide treatment. So does this mean we have less than 1 insect? No, it doesn't, remember, because P is in thousands. All right. So really what I'm looking at here is that this actually represents about 527 insects. Okay. So each one of these would say be multiplied by 1,000. And that would be insects. And you can do this now. You can also do it at the end after you do the differences. It's sort of up to you. Okay, both would work, because multiplying each of them separately by 1,000 would be like multiplying the average rate of change by 1,000 at the end. All right, so this one times 1,000 is going to move that. So I'm going to have 48,146.161 insects. This one times 1,000, 527.313 insects. So now we're going to set up our average rate of change. Now this is one of those things, remember, this is the change in Y over the change in X. So it's important for you to understand that the change in your P values will be over the change in your D values here. So that's insects over days, because our units are going to be insects per day, and that's what we need to remember too, or we need to know that. So I always recommend that you put the units in your math. So in my days, I like to start with the larger. So this is 4 minus 1 days, which is going to give me 3 days. And then I'm looking at so the 4 number has to go first, and that is this 527.313 minus the insect number that goes with the 1, which is the 48,146.161 insects. So let's subtract 527.313 minus 48,146.161. We should, of course, expect this to be negative. And I get negative 47,618.848. Now dividing that by 3, I'm going to now get negative 15,872.949. And my units are now insects per day. So what the negative means is that there's an average decrease of this many insects per day, an average decrease of this many insects per day. And so that kind of makes sense because we should realize we were dealing with a decay model. So we would expect the average rate of change here to be a decrease. All right, so from day 1 to day 4, after application of the product, there is an average decrease of about 15,872.942 insects per day. So on average, during that time period, there was a decrease of not quite 16,000 insects each day. So there would have been more the first day, a little less the second day, a little less the third day, less than that the fourth day. But the averaging of all of those quantities over time, over that time period, gives us just under 16,000 insects per day were basically killed. All right. Here is a practice problem for you to try. Pause your video. Let's take a look. All right. Let's look at another one. Another one to try. Pause the video. All right, let's take a look. All right. So this brings us to the end of this lesson, and I hope that you have a wonderful, wonderful day. Bye-bye.